going to do the Lagrangian problem of trying to lift up a piano up onto a stage, choosing two pulleys. And so we want to figure out, so the idea is that Sean is pulling it up, then Sean loses grip and it starts to fall. So we want to know how quickly does it fall, and if you are some certain distance away. Way over here, let's say in the back of the auditorium. Can you yell and have the sound get there in time to warn Sean so his foot doesn't get crushed with the piano? Okay. All right, so let's, part A, let's first do the Lagrangian. So we need our kinetic energy and we need our potential energy. So potential energy, maybe we should just do that first. That's a little easier. So we have the mass of piano, G and Y. So I'm going to just say my Y coordinate looks like that. Okay, so now technically this pulley will also go up as well. I guess we will use that as well. Okay, so it doesn't really matter. This height is going to cancel out when we plug into Lagrangian, but we could say that then it's M1 G. Y will be the height of the piano plus L. Okay. If you left this off in the gravitational part, I didn't take off. Okay, so our kinetic energy is going to be just the kinetic energy of the piano. So 1/2 m piano y dot squared. And then for the pulleys, there's going to be a rotational energy. So we should also put in 1/2 m1 y dot squared, because it will be moving up and down too. And then the rotational energy, so 1/2 m2, let's do 1/2 I2 omega 2 squared plus 1/2 I1 omega 1 squared. Okay, so for both of these are a disk, right? So our moment of inertia is just 1/2 m2 r2 squared omega 2 squared, and we have another 1/2 there. 1/2 m1 r1 squared omega 1 squared. And now the key thing, right, is to realize that this r1 omega 1 is the same as, right, we use this v as omega r. So this is the same as y dot, right, as these are rotating. This angular rotation times the radius is the same as the vertical change in the height. So y dot. Okay. So then we have 1/2 mp y dot squared plus 1/2 m1 y dot squared, because that pulley is actually moving up and down. Again, I didn't take off if you missed that part. 1/4 m2 y dot squared plus 1/4 m1 y dot squared. Okay, so then if we have, let's just combine, oops, sorry, that's m1. So we actually have 1/2 mp y dot squared plus 3/4 m1 y dot squared plus 1/4 m2 y dot squared. So just to simplify out, we'll take the 1/2 there and we'll keep the y dot on that side. Okay, so then we have mp plus 3/2 m1 plus 1/2 m2. And that's our kinetic energy. Okay, so our Lagrangian is T minus U. So just general test-taking strategy. Like a lot of people were just thrown by this. So, put something reasonable. Put that my potential energy is mgy and that my kinetic energy is that. Even if you didn't get any of the rotation part, you're going to lose 4 points, but you could still go through and solve the rest of it, right? So I'm not going to take off more than 4 points for missing these things. So you need to be thinking, point strategy when you're taking exams. Okay, so we have 1/2 mp plus 3 halves m1 plus 1 half m2 y dot squared minus our potential energy, mp gy minus m1 g y plus L. Okay, so let's put that on the next sheet and we can crank through. Okay, 1 half mp plus 3 halves m1 plus 1 half m2 y dot squared minus mp gy minus m1 g y plus L. Make sure we got that right. 3 halves, 1 halves. Okay, that's our L. So there is only one coordinate, right? So this thing where we're relating the angular velocity theta to, or omega to the distance traveled in the pulley means that we can reduce this to just one coordinate. Okay, so now we want to apply, for part B, we want to apply the Euler-Lagrange equation. Okay, so we need to get dl dq dot is going to be, so that 2 comes down, cancels the half. So we just get this effective mass here, mp plus 3 halves m1 plus 1 half m2 y dot. Okay, and then dl dq is just going to be this with respect to y, so we get minus mpg for that one. And here this is m1gy minus m1gl. So this is really just a constant, doesn't come out. So we get mpg in this term. When we take the derivative with respect to y, we're just going to get m1g. Okay, and now we need to do ddt, dl dq dot is going to be this effective mass again, mp 3 halves m1 1 half m2 y double dot. Okay, so now we can use our Lagrangian equation, right? So our Euler-Lagrange, dl dq dot minus dl dq equals 0. Okay, so we have mp plus 3 halves m1 plus 1 half m2 y double dot. And I'm just going to bring that over to the other side, equals minus mp plus m1 g. Okay, so I just brought that down over onto that side and factored out the g. So then our acceleration, y double dot, equals mp plus m1 divided by mp 3 halves m1 plus 1 half m2 times our acceleration of gravity. So let's just give this, call it m ratio or something, so we don't have to keep rewriting that over and over. So now if we want to get our part C, is asking for equation of motion, determine the time it takes to hit the ground. Okay, so C, if we have y double dot equals our m ratio g, then y dot equals the integral ratio dt. So y dot equals negative m ratio gt plus the constant, and that constant is going to be whatever our velocity is when t is 0, right? So this is actually our initial velocity. Okay, and then our position is the integral of y dot dt, and so that's going to be negative m ratio g 1 half t squared v0t plus another constant. And then again, if we let t equal 0, this term goes away, this term goes away. So this physically is our initial position, y0. Okay, so we get y as a function of time is y0 plus v0 t minus 1/2 m ratio g t squared. So very similar to what we have normally, right? For our kinematic equation just under the acceleration of gravity, except for this factor of the mass ratio. Okay, and let's just calculate what that is. So our mass of the piano is 150. M1 equals 10, and M2 equals 15. So our M ratio is P plus M1 divided by P plus 3/2, so 1.5 times M1 plus 0.5 times M2. So pretty close. M ratio is 0.9275. We'll just kind of keep that so we don't have to plug that in again later. Okay, so if we want to get the time, so basically it means that the effective gravity is like 92% of what it would be on without the pulleys, right? If the piano was just freely falling. Okay, so our y0 is going to be 3 meters, right? So the piano's lifted up to 3 meters, and when Sean loses his grip, the initial velocity is 0 because it's dropping from rest, and the final velocity would be 0. So we have negative y0 divided by negative 1/2 m ratio g equals t squared. We want to find how long it takes to drop. Okay, so let's go back to our screen over here. So y0 is 3, g equals 9.8. And so we get the square root of y0 divided by 0.5 times m ratio times g. Okay. So we get 0.812 seconds for the piano to drop. Okay, and then, so do you have time to warn Sean? Okay, so if you're going to yell, and Sean has got to hear it, and that's 30 meters away. Okay, and then Sean also got to move his foot out of the way. Okay, so this is just, constant velocity motion, right? So we can just use velocity is distance over time. There's no acceleration in the speed of sound. So the time that we'd want to solve for is the distance divided by the speed of sound. So 30 meters divided by the speed of sound, 340 meters per second. We could go back to our screen here. 30 divided by 340. Oops. 0.088. Okay. So definitely enough time if you can yell right away, but usually reaction time is, half a second or something. So you'd have to react really quickly and yell in order to warn Sean. That is that. So just to recap, right, really the hard part is getting these terms, right, figuring out in terms of the potential energy. The tricky part might be trying to account for the fact that this pulley is going to move up. I did not take off if you missed that and you just did mass of the piano. Kinetic energy, this part is straightforward, right? The 1/2 m y naught squared. You need to think about the rotational energies of the two pulleys and then be able to make this connection that R omega is related to, the amount that these are turning is also related to the amount that the pulley goes up and down, exactly as it was in the practice final exam problem. And then there's also this additional kinetic energy term from M1 if it's moving basically with the pulley. So again, I didn't take off if you missed that. So it's really only one extra term from what was in the practice final, right? Because there were two pulleys there. And again, just kind of triage. If you don't know what to do, even just doing this, right? That is better than nothing. It's just like a free falling piano. You're going to lose 3 points here, maybe, but the rest of it you could get. So, yeah, so you want to be thinking about that as you're finishing exams or taking exams, right? How can you maximize your points